Hello guys, IBM is here with another episode of magnetic fields and electromagnetic induction. I think this is going to be part 14. Starting with question 37, this is going to be part 14 of the past paper questions. A uniform magnetic field has constant flux density B. A straight wire of fixed length carries a current I at an angle theta to the magnetic field as shown in the figure. So we see that the magnetic field is at an angle theta to the current. So we always need the magnetic field or the component of the magnetic field perpendicular to the wire or to the conductor. So if B is the magnetic field, perpendicular to the conductor is going to be B sine of theta. Okay. The current I in the wire is changed, keeping the angle theta constant. On the figure, sketch the graph to show the variation with the current I of the force F on the wire. So we know that force is equal to B sine of theta because now they've given us the angle between the field and the current, and yet we need always the component of B perpendicular to the current, which is B sine theta. So the angle theta is constant. Of course, the length of the wire is constant. The current in the wire is what is being changed. So that means B is not changed. So it means that F is going to be directly proportional to the current. And therefore, this means as I increases, the current is going to increase. So this means this is going to give us a straight line with a positive gradient. If F is proportional to I, since B, L, and theta are constants. It means when F is 0, when I is 0, F is 0. When I increases, F increases. So this is going to be a straight line through the origin. So that will be a straight line through the origin. The angle theta between the wire and the magnetic field is now varied. The current I is kept constant. So the current is kept constant, but is theta which is varied. Again, going back to the same equation, F equals to B sine of theta. So B is constant, I is constant, L is constant. It's only the angle which is varied. So F is directly proportional to sine theta. And we know that when theta equals to 0, F is going to be 0. So the graph starts from the origin. And when theta equals to 90 degrees, sine of 90 is 1. So F is going to be equal to maximum. So this becomes maximum. So the graph should have reached a maximum value of F at theta equals to 90 degrees. Of course, we notice that when theta equals to 30 degrees, F is going to be half of the maximum value. So we should notice that if we say the maximum value is this one here, if I say that this is the maximum value for my graph at 90, at 30, it should be half. So I'm trying to estimate half around here. Half. So it should be around there. At 30, it should be approximately half of the maximum value. So if the maximum is somewhere here, at 30 it should be half. So this is not a straight line, this is a curve because it is sinusoidal, so this should be a curve of that pattern. So the graph is a curve of decreasing gradient and maximum at, because sine 30 is a half, so it means a maximum. If it's maximum at 90 and at 30 degrees, it should be approximately half. So the graph would look like that. A uniform magnetic field is directed at right angles to the rectangular surface PQRS of a slice of a conducting material as shown here. So it's perpendicular to the slice as shown here. The electrons are coming from this side, which means the current is in the opposite direction. The current is in the opposite direction because current moves in the opposite direction to that of the electrons. Electrons moving towards the side SR enter the slice of conducting material. The electrons enter the slice at right angles to the side SR, which also means the current is flowing at right angles to the end to the side SR. Explain why initially the electrons do not travel in straight lines across the slice from side SR to side PQ. So when the electrons enter into the slice, because they will be entering perpendicular to the magnetic field, they experience a force whose direction can be predicted by Fleming's left-hand rule. As long as the charged particle moves perpendicular to the magnetic field, it experiences a force. So I would say there is a force. There is a force on an electron due to the magnetic field. There is a force on an electron due to the magnetic field, and the force on the electron is perpendicular to the magnetic field. Is perpendicular to the magnetic field and the direction of the electron. And the direction of the electron given by Fleming's left-hand rule. So there is a force on an electron due to the magnetic field, and the force on the electron is always perpendicular to the magnetic field and the direction of the electron as predicted by Fleming's left-hand rule. Explain to which side PS or QR the electrons tend to move. So do the electrons tend to move towards PS or QR? Let's look here. So note that when using Fleming's left-hand rule, the second finger must point in the direction of the positive particle or the direction of the electrons. The direction of the current. So when using it for electrons, we reverse the second finger. If we are using it for negatively charged particles, we reverse the second finger in Fleming's left-hand rule. So thus, you'll observe that with the first finger pointing in the direction of the magnetic field, which is actually downwards, and the second finger pointing in the opposite direction to the electric field, which is towards the right, by all means, if you use your left hand, you notice that the thumb must point away in that direction as represented here. That should be into the page. If you hold your page vertical, it will be into the page. The thumb should be into the page using Fleming's left hand rule. So that means it should be pointing towards end QR. So I will simply say by Fleming's left hand rule, by Fleming's left hand rule, the electrons move towards QR. Okay. A constant current is maintained in a long straight vertical wire A Hall probe is positioned a distance r from the center of the wire, as shown in the figure here. Explain why when the Hall probe is rotated about the horizontal axis xy, the Hall voltage varies between a maximum positive value and a maximum negative value. In other words, why does it change direction? So the Hall voltage, of course, depends on the angle between the plane of the probe and the magnetic field. That's why we say the Hall voltage VH is equal to BI over NTQ. That is, if B is perpendicular to the plane of the probe. But if it is not perpendicular, it could be B sine theta or B cos theta, depending on the position of the angle. So the full one could be maybe BI sine of theta divided by NTQ, which means that the Hall voltage also depends on the angle between the plane of the probe and the magnetic field. If the angle between the plane of the probe and the magnetic field is 90 degrees or perpendicular, then the Hall voltage is going to be, in this case, if we take sine theta, sine of 90 is 1, so the Hall voltage is going to be maximum. If the angle between the plane of the probe is 0, or the plane of the probe is parallel to the magnetic field, then the Hall voltage goes to 0. And when we move in the opposite direction, then it goes to another maximum value, which is going to be negative. So we shall say that the Hall voltage depends on the angle between the plane of the probe and the magnetic field. The Hall voltage depends on the angle between the plane of the probe and the magnetic field. So the Hall voltage depends on the angle, and then the Hall voltage is maximum when the plane and the magnetic field are perpendicular to each other, and 0 when the plane and the magnetic field are parallel to each other. When the plane and the magnetic field are perpendicular to each other. And 0 when the plane and magnetic field are parallel to each other. Of course, it will be maximum twice because of different angles, different directions. It will be maximum twice, but of course it will be 0 whenever the plane of the Hall probe is parallel to the magnetic field. So it depends on the angle between the plane and the probe. When it is maximum, when the angle is 90 degrees, then it is maximum. So it can be maximum positive, or it can be maximum positive or maximum negative. The maximum Hall voltage VH is measured at different distances r. Data for VH and the corresponding values of R are shown in the figure 5.2. That is, here we have VH, data for VH, and data for R. And you notice that as R increases, VH actually decreases. It is thought that VH and R are rated by an expression of the form VH equals to K over R, which means VH times R should be equal to a constant K, where K is a constant. Without drawing a graph, use data from the figure to suggest whether the expression is valid. So we want to check whether the expression is valid. So I'll just manipulate this to make a VHR. I'll just get product of VHR to see if the values are either the same or they are different to the same number of significant figures. Okay, so I'm going to check VH times R to see if it is a constant. So we are going to check if VH times R equals to a constant. Okay, so I have the first one is, let's say 0.290, that is volts times 1.0 centimeters. This gives us 0.290 volts centimeters, or 0.3, I think that is approximately 0.3 volts centimeters to one significant figure. I can check the second one, 0.190 volts times 1.5 centimeters, 0.19 times 1.5, that is 0.285 volts centimeters, which is approximately 0.3 volts centimeters to one significant figure, or it is approximately 0.29. I will check the third one, 0.140 volts times 2.0 centimeters. I think this is obvious. This is 0.280 volts centimeters, which is approximately 0.3 volts centimeters. I will check one last one, 0.097 volts by 3.0 centimeters. This is equal to 0.097 times 3. That is 0.291 volts centimeters, which is approximately 0.3 volts centimeters. So you have two ways of thinking about this. You could say to two or to three significant figures, V times R, VH times R is not constant, so the suggestion is not valid. I could say to two or three significant figures. Let me just set to two significant figures. To two significant figures. To two significant figures, VH times R is not constant. It's not constant, so the suggestion is not valid. The suggestion is not valid. Or now check for one significant figure. It is valid. So or I can set to one significant figure, VH times R is constant. So the suggestion is valid. So you can either give when it is not valid, or you decide to give it as being valid, but you have to be very specific for this part here. A graph showing the variation with 1 over r of VH is plotted. So you notice that VH is directly proportional to 1 over r according to that expression here. So this is a straight line. Suggest the feature of the graph that suggests that the expression is valid. So this is going to be a straight line. It should be a straight line passing through the origin. If a graph plotted was of VH against R for this equation here, it will be an exponential graph, but this is VH against 1 over R. So that as 1 over R increases, VH also increases. So that is a straight line. So you should not confuse a VH against 1 over R with a VH against R. The whole probe in A is now replaced with a small coil of wire connected to a sensitive voltmeter. The coil is arranged so that the plane is normal to the magnetic field of the wire. State Faraday's law of electromagnetic induction and hence explain why the voltmeter indicates a zero reading. The whole probe is now replaced with a small coil of wire connected to a sensitive voltmeter. The coil is arranged so that its plane is normal to the magnetic field of the wire. State Faraday's law of electromagnetic induction and hence explain why the voltmeter indicates a zero reading. Okay, so we know what Faraday's law states. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. So magnitude of induced EMF is proportional to the rate of change of the magnetic flux linkage. That is according to Faraday's law. Because now we are holding a coil in the position where we had the whole probe and it is not moving, it means there is going to be a constant magnetic field, of course, at the position of the coil. That means the magnetic flux linkage is constant and therefore there will be no induced EMF. So we could say there is a constant magnetic field due to the wire. Because the wire is carrying direct current, there will be a constant magnetic field. There's a constant magnetic field that is due to a constant current. I'll put this in brackets. Due to a constant current. So the magnetic flux linkage of the coil does not change. The magnetic flux linkage of the coil does not The magnetic flux linkage of the coil does not change. Hence, no induced EMF. So holding a coil there or replacing the whole probe with a coil, and yet the current in the wire is constant, the magnetic field is constant. A constant magnetic field does not induce an EMF, so the magnetic flux linkage of the coil is constant. The magnetic flux linkage of the coil does not change, so there will be no induced EMF. State 3 different ways in which an EMF may be induced in this coil. So if we placed a coil here in this position, if now we put here a coil in this position here, to induce a current in it, one, we can switch on and off the current in the wire. Switching on changes the current from a certain value to 0. Then switching off changes from a certain value to 0. Switching on changes the current from 0 to a certain value. So switch the current on or off. That's number one. Number two, you can move the wire towards or away from the coil, or you move the coil towards or away from the wire. Number three, you can rotate the coil around. You can rotate the coil so that the magnetic flux linkage changes, or you can replace the current in this wire from DC to alternating current. Alternating current will create a changing magnetic field, which will cause a change in magnetic flux linkage. Or you can vary the current in the wire. Maybe you have a variable power supply, even though it is DC, you can increase the current or decrease the current. So you are varying the current in the wire. All those changes will change the magnetic flux, the magnetic field, and also change the magnetic flux linkage, thereby inducing a current in, thereby inducing an EMF in the coil, which is placed in the position of the Hall probe. Okay, so there are several ways in which an EMF is going to be induced there, and one of them is vary the current in the wire. Vary the current in the wire. The second one, switch on. You could switch on and off the current in the wire. The other one would be use alternating current. Use alternating current instead of DC. Another one could be rotate the coil. In all cases, rotating the coil, you are trying to cause motion, so that you are causing cutting of the magnetic field. Or you could say move the coil towards or away from the wire carrying current. Move the coil towards or away from the wire carrying current. Okay. Negatively charged particles are moving through a vacuum in a parallel beam. The particles have speed v. The particles enter a region of uniform magnetic field of flux density 930 microteslas. Initially, the particles are traveling at right angles to the magnetic field. If the particles are traveling at right angles to the magnetic field by Fleming's left-hand rule, they will experience a force which is perpendicular to the magnetic field and also perpendicular to the direction of motion of these particles. The path of a single particle is shown here. Okay, so it's an arc of radius 7.9 centimeters. The negatively charged particle Particles follow a curved path of radius 7.9 centimeters in the magnetic field. A uniform electric field is then applied in the same region. So they are now adding a uniform electric field in the same region. For an electric field of 12 kilovolts per meter, the particles are undeviated. So when E is 12 kilovolts per meter, the particles are undeviated as they pass through the region of the fields. On the figure, mark with an arrow the direction of the electric field. Okay, so to start with, the particles for the magnetic field alone, they are curving upwards. So since the magnetic force is towards the top, so because the curve due to the magnetic field is upwards, it means the magnetic force is upwards. The magnetic force is upwards. For no deflection, for no deviation, when we introduce an electric field for no deflection, then the electric field is going to be downwards. I mean, the force to the electric field must be downwards. So the force to the electric field, Fe, should be downwards. So since the magnetic force is upwards, that is towards the top of the page, for no deflection, the electric force must be pointing to the bottom of the page, that is in the opposite direction. And we know that the direction of the electric force is always opposite to the direction of the electric field for a negatively charged particle. The direction of the electric force on a negatively charged particle is in opposite direction to that of the electric field. So since the electric force is downwards, then the electric field must be upwards because the particle into consideration is negative. Therefore, it means the electric field is going to be upwards. Do not forget that the electric field lines always point from high potential to low potential. So if the particle is negative and the force is downwards, the force on a negatively charged particle is always in the opposite direction to the electric field. So the electric field must be in this direction here. Therefore, I can now remove all these other lines to leave what is required. So E is going to be upwards. Then calculate for the negatively charged particle the speed v. So for no deflection, we say that the magnetic force equals the electric force. Magnetic force equals to electric force. So that means BQV equals to QE, which means that V equals to E divided by B. We can make substitution. E was 112 kilovolts per meter, that is 12,000. And B was 930 microteslas, so that is 930 times 10 to the power of minus 6. So we have 12,000 divided by 930 exponent minus 6. So that is 1.29 times 10 to the power of 7. Meters per second, or you can write 1.3 times 10 to the power of 7. Then the ratio charge over mass. So since the magnetic force provides the centripetal force, magnetic force provides centripetal force. So it means we shall say BQV is equal to mv squared over r. So we want charge over mass. So Q over m is going to be a V divided by R times B. Then we can now make a substitution. So this is going to be V was 1.29 times 10 to the power of 7. The radius, what is R? R is 7.9, so that is 7.9 times 10 to the power of minus 2. And then B is 930 times 10 to the power of minus 6. So from my calculator, 1.29 exponent 7 divided by 7.9 exponent minus 2 divided by 930 exponent minus 6. So that is 1.7558, which is approximately 1.8 times 10 to the power of 11. So that is 1.8 times 10 to the power of 11 coulombs per kilogram. Okay, so I want part 14 to stop at this point. See you in part 16. Bye bye.